Hello everyone, you are most welcome to the Universe Science Scholars Academy, USSA. In today's video, I want us to specifically learn how to calculate the oxidation state or the oxidation number of an atom in a compound. So, the first things first, it is very much necessary for you to understand the definition of oxidation state. An oxidation state can simply be defined as the net charge that would be left on an atom if a compound were completely ionic. Or specifically, we can have a compound and we decide to ionize all the other elements in the compound and we only remain with one atom of an element. Okay? For example, let's say we had this compound and we decide to ionize this and we only want to get the oxidation state probably that is left on manganese, and that is X. We are trying to look for that oxidation state left on manganese, which we are referring to as X specifically. So if you're interested, please watch to the very end of the video. So before we calculate any oxidation state specifically of any element, there are some rules that I want you to always be having at the back of your mind. The very first rule that you should be having at the back of your mind, that all the free elements specifically have an oxidation state which is equals to 0. It could be sodium as a free element, it could be oxygen that is behaving as a free element, it could be magnesium, and so on and so forth. All of this will be having their oxidation states to be 0, or rather the oxidation state of a free element specifically is 0. Secondly, if we are having simple ions, their oxidation states are also equals to their charge. For example, if we are having an ion of sodium, its oxidation state is +1. Note it is a plus, not a superscript plus. This is specifically wrong. Okay? It could also be specifically magnesium. This is also going to be having an oxidation state of +2. It could also be an anion, and this is having an oxidation state of -1, and so on and so forth. For example, aluminium would also be having it as +3. Then the third rule will be for oxygen. Normally, its normal oxidation state is always going to be 2, -2 specifically. In water, its oxidation state will always be considered as 2. Even in carbon dioxide, we shall always be considering its oxidation state as 2. But we are regarding an exception specifically for some specific compounds, like if we are having a peroxide, like we are having hydrogen peroxide, oxygen in this case will be bearing an oxidation state of -1. And even if we are having other compounds similarly, like we are having oxygen difluoride, this would also be having an oxidation state of +2, and not specifically the usual one. So this one is when we are considering it normally in the normal oxidation state, it will always be having a -2. These are the only exceptions we can be considering for now. Hydrogen, on the other hand, will always be having the oxidation state of +1. Even if we are having it specifically with water, it would also be having an oxidation state of +1. Alright? But then if we are considering it in a metal hydride, specifically, it will be having an oxidation state of, hydrogen will now be having an oxidation state of -1 for metal hydrides. For example, in sodium hydride, we shall always have oxygen having it is oxidation state as, we shall always be having hydrogen having its oxidation state as -1. Alright, now here is a point that I want everyone to keep a little bit of so much vigilance, and I would always be naming this the golden rule. So how does the golden rule apply? That if you are given specifically a compound, or rather it could be an ionized bit of a compound, and they're asking you to calculate the oxidation state, please note how many atoms of a specific element are you having. For oxygen, there are going to be 4, and that means we shall be considering the number times its normal oxidation state, and at the end of it all, we shall equate the sum. We shall be equating the sum specifically to the general. Shall be considering specifically the sum and considering it to the general state, or rather charge we have, which is going to be -2. So with that small knowledge, I want us to start with calculating specifically for the oxidation state of sulfur in the two of these. So when we are also going to first consider in our answering, the first thing that we shall consider is we shall first let the oxidation state of our sulfur to be a certain letter X. So we shall say X plus, what is the oxidation state of oxygen? It is -2. But how many atoms are there? There are 4. So it's going to be 4 times the -2, which will be equals to the general charge, which we have as -2. Alright, so this will be an overall of about -2 plus 8, which will be equals to 6. So sulfur is having its oxidation state of -6 specifically. I mean +6. Always never forget to put the sign. Okay, we can do another example. These mistakes of forgetting the sign or putting a sign to be a superscript, please, it should always be on the same line with the integer that you have assigned it. Then another example that we could consider is where we are having specifically dichromate. So here we would also let the dichromate be having its oxidation state specifically as maybe M. But then since there are 2 atoms, to be times 2, and oxygen here, we shall be having -2 times 7. So we shall be having 2M minus specifically -14, which is got from here, and to be equaling, or we shall be equating it to -2. So 2M specifically is going to be equals to -2 plus 14, and 2M is equals to 12, and M is going to be plus 6. So if we were to tell specifically what the oxidation state of chromium here would be, it would be plus 6 finally. Alright, so we could be having another one like the one that we had before, whereby we're considering potassium. Specifically, we shall be considering potassium permanganate 7. So we shall be having this into consideration. The other tip that I would like us to be having before we work out this is, normally whenever we are having the metals of group 1, for example, we can be having lithium, we can be having potassium, all of this will be always having their oxidation states at +1. And when we're having the group 2 metals specifically, for example, like we can have magnesium, we can have calcium, we can have barium, they will always be having their oxidation state of the normal oxidation state as +2. So if we are to attack this specific number and get the oxidation state, what you'll be realizing specifically here is that number 1, we are trying to get the oxidation state of manganese. So the first thing first, we shall be letting our manganese to have an oxidation state which we don't know. The unknown is X, and we do know from this specific guide rule that potassium, since it is a group 1 metal, to be having a normal oxidation state of 1, and oxygen here we are going to be having -2 times the number of atoms, which is 4. So at the end of it all, we are going to be summating the whole and equating it to our oxidation, or rather the general charge, which is 0. So this is going to be x plus 1 for potassium minus 8 is equals to 0. So x minus 7 is equals to 0, and x is equals to +7. So therefore, the oxidation state or oxidation number of manganese here specifically is +7. So that will be the end, and I would like everyone to please keep on trying out to use that knowledge to calculate the oxidation state, because in our next video we shall specifically be learning how to write and balance the half equations of redox reactions specifically. How to write and balance the redox equations. That is what we shall be covering in our next video. So thank you for watching. Please like, share and subscribe. I remain Master Andrew, USSA. Let's explore the universe together.